Part A. Use long division to factorise x cubed minus a cubed in the form x minus a times q1 of x, where q1 of x is a quadratic. So if we write x cubed minus a cubed equals x minus a times q1 of x, we recover q1 of x by performing the long division x cubed minus a cubed divided by x minus a. And the division proceeds in the usual way with a little additional color coding to indicate which operations are taking place. And so we see that we can write x cubed minus a cubed as x minus a times x squared plus ax plus a squared, where x squared plus ax plus a squared is q1 of x. Part B. Hence factorise x cubed plus a cubed in the form x plus a times q2 of x, where q2 of x is a quadratic. So from part A, we have that x cubed minus a cubed equals x minus a times x squared plus ax plus a squared. And to use that result, we can rewrite x cubed plus a cubed in the form x cubed minus c cubed, where c is some constant, and then use the result that we showed in part A. So we have x cubed plus a cubed, which we can write as x cubed minus a cubed. And now we note that minus a cubed equals minus a all cubed. And so we have that x cubed plus a cubed equals x cubed minus a all cubed, which is in the form x cubed minus c cubed, where c equals minus a. And we can factor that quantity using the result from part A as x minus a times x squared plus minus a times x plus minus a all squared, which simplifies to x plus a times x squared minus ax plus a squared. And so we have that x cubed plus a cubed equals x plus a times x squared minus ax plus a squared, and that is true for all x and a in R. Part C. Use the result from A to show that if x cubed equals a cubed, then x equals a. Now, we might think that this isn't a result that we need to show. Can we not just cube root both sides to show that if x cubed equals a cubed, then x equals a? Well, in fact, we can do that, but this result shows that we can do that validly. It shows essentially that the cube root function exists. And we should note that we have to be a little careful with a problem of this kind, because if we consider x squared equals a squared, then it is not true to write that x squared equals a squared implies that x equals a, which is the result that we would get if we naively took the square root of both sides. In fact, in this case, we have that if x squared equals a squared, then x equals a, or x equals minus a. And we can get that result if we rewrite x squared equals a squared as x squared minus a squared equals 0. We factorise using difference of two squares identity. We generate two separate linear equations, which we solve to find that x equals a or x equals minus a. And we can attack this problem in a similar way. we have that x cubed equals a cubed implies that x cubed minus a cubed equals 0. We apply the result from part A to find that x minus a times x squared plus ax plus a squared equals 0. From that, we generate the two separate equations x minus a equals 0 or x squared plus ax plus a squared equals 0. And we can solve the first, x minus a equals 0, to find that x equals a. And that leaves the question, does the equation x squared plus ax plus a squared equals 0 have any additional solutions? And we can answer that question by completing the square in the quadratic and solving the resulting equation. So we start with 0 equals x squared plus ax plus a squared, and we complete the square to find that x plus a over 2 all squared plus 3a squared over 4 equals 0. And now we consider the two important facts. X squared is greater than or equal to 0 for all real x. X squared equals 0 is equivalent to x equals 0. And now we note that if x plus a over 2 all squared plus 3a squared over 4 equals 0, then x plus a over 2 all squared equals minus 3a squared over 4. But bearing in mind the two important facts that we just noted, we see that x plus a over 2 all squared is greater than or equal to 0, and that minus 3a squared over 4 is less than or equal to 0. But the only way that that can be true is if both quantities separately are equal to 0. Because if x plus a over 2 all squared was greater than 0, it could not be equal to a quantity less than or equal to 0. And a similar argument applies for minus 3a squared over 4. And so we have that x plus a over 2 all squared equals minus 3a squared over 4, and both equal 0. And we solve the equation on the right to find that a equals 0, bearing in mind the second important fact marked in green, x squared equals 0 is equivalent to x equals 0. And we solve similarly the equation on the left to find that x equals minus a over 2, but since a equals 0, then x also equals 0. And putting those two results together, we see that x equals a and both equal 0. But the important point that we have shown here is that x equals a. We have an identical solution to that which we had from the equation x minus a equals 0. So the only solution to the equation x squared plus ax plus a squared equals 0 also has the form x equals a. And so we have shown that x cubed equals a cubed implies x equals a for all x and a in R as required. And it is worth noting that this result shows that for real x, f of x equals x cubed is a one-to-one function. It is also an onto function, which means that we can make any real number by cubing some real number, and together that tells us that we have an invertible function, with the inverse function being f of x equals the cube root of x. Part D. Hence solve the equation 27x cubed plus 27x squared plus 9x minus 19 over 8 equals 0. And since this is a hence question, we must use the result from part C to solve the equation. Now, since we have to use the result x cubed equals a cubed implies x equals a, that seems to imply that we can write the equation above in that form, although it's not immediately obvious how we will do that. Now we note that we have terms in x cubed, x squared, x, and also a constant, and so the expression looks like the result of a binomial expansion, where the relevant binomial expansion is x plus c all cubed equals x cubed plus 3c x squared plus 3c squared x plus c cubed. And in order to see how that applies here, we will look at only the first three terms in the equation and compare that to the first three terms in the binomial expansion. So we want to compare 27x cubed plus 27x squared plus 9x to x cubed plus 3c x squared plus 3c squared x. But we can see that we could never make those two terms equal to each other because the leading coefficients differ. 27 in the case of the equation, 1 in the case of the binomial expansion. However, all is not lost because we can factor 27 out of the equation terms to produce 27 times x cubed plus x squared plus 1/3 x. And now we can see that we have a chance of making the term in the brackets equal to the term from the binomial expansion. And if those two terms are going to be the same, then we need 3c equal to 1, 3c squared equal to 1/3, which means that 3c equals 1 and c squared equals 1/3, which we solve to see that c equals 1/3 and c equals plus or minus 1/3, and these two sets of solutions are consistent as long as we take c equals 1/3. And on setting c equal to 1/3, the binomial expansion gives us x plus 1/3 cubed becomes x cubed plus x squared plus 1/3 x plus 1/27, from which we find that 27x plus 1/3 all cubed equals 27x cubed plus 27x squared plus 9x plus 1. And we note that we have generated the first three terms in the equation that we have to solve. And bearing that in mind, we take the expression from the equation and we rewrite it as 27x cubed plus 27x squared plus 9x plus 1 minus 1 minus 19/8, where we have added 0 in the form plus 1 minus 1. And from this, we get 27 into x plus 1/3 cubed minus 27/8, due to the fact that these terms, because of this equation, become 27 into x plus 1/3 cubed, and these terms simplify to minus 27/8. And so we have that 27x cubed plus 27x squared plus 9x minus 19/8 equals 0 implies that 27 times x plus 1/3 all cubed minus 27/8 equals 0, which gives us that x plus 1/3 all cubed minus 1/8 equals 0, so that x plus 1/3 all cubed equals 1/2 cubed. And so using the result from part C, we have that x plus 1/3 equals 1/2, so that x equals 1/2 minus 1/3, which equals 1/6. And the result from part C tells us that that is the unique solution to the equation in question, so we are done.